Hello, my name is Vardhan and I want to discuss with you a few concepts about gravitation. When I say the word gravitation, what comes to your mind? Probably the earth. It is the source of all the gravity that we feel. The sun, maybe. The solar system, space. Some of you may even think about Newton and how he discovered the laws of gravitation. Well, before Newton as well, there were a lot of people who contributed to the research of gravitation. Some notable people were Copernicus, Galileo, Tycho Brahe. Well, I'm sure you may have heard about Tycho Brahe. But Tycho Brahe sat on a remote island somewhere near Denmark and for over 2 decades he observed the sky. He noted down which stars are observed where and when, which planets are observed where and when, and he tabulated this data nicely. Towards the end of his career, at the beginning of the 17th century, Tycho Brahe took Kepler as his assistant. Kepler was a mathematician and Kepler tried to identify patterns in the data that Brahe had collected. And Kepler came up with 3 laws, the famous Kepler's laws of planetary motion. So what are the Kepler's 3 laws of planetary motion? The first is the law of elliptical orbits. Orbit is the path which a planetary body like the Earth follows around a star like the Sun. So what is an ellipse? It is sort of a squeezed circle. It looks like this. Okay. This vertical line, dotted line that you see divides the ellipse into identical symmetrical parts, and a horizontal line. We have 4 symmetrical parts of the ellipse. An ellipse has 2 foci. Okay, they are symmetrically placed about the vertical line. The half of this vertical line is called the semi-minor axis. Okay, and the larger the horizontal side, you guessed it, it is called the semi-major axis. So what Kepler proposed was that the sun sits on one of these foci. So let us say that the sun sits right here. And the earth follows this elliptical path around the sun. So our earth is going to move along this elliptical path. This is Kepler's first law of planetary motion, the law of elliptical orbits. So the first law of planetary motion is the law of elliptical orbits. What is the second law of planetary motion? Well, this is slightly involved, so pay more attention here. On the same ellipse, I am now going to locate sun at one of the foci. So let us say this black body that I have drawn here is the sun, and a small tiny planet like Earth is going around this elliptical orbit. Okay, we are now going to draw a line connecting the sun and the Earth. So this is our sun here, and I will use E to denote Earth. If we draw a line, if we draw a line connecting the Sun and Earth, okay, this is called the radius vector. Let us give it a direction. So it starts from the Sun and it points in the direction of Earth. Okay, this radius vector, I am going to say, as the Earth goes forward, I am going to keep a track of this radius vector. So let us say after some time, let us say after few days, the Earth is at a different location along this orbit. So this is the radius vector r at time t equal to 0. So let us call it r0, and the radius vector after 2 days, let me call it r2. So you see that there is some area that is demarcated by these two vectors. So between r0 and r2, and I am going to hash that area. So this, I would say, is the area swept by the radius vector in 2 days. What Kepler proposed was that no matter where the Earth is on this orbit, the area that this radius vector sweeps in 2 days will remain the same. So for example, after let us say a couple of months, the Earth is at some other point on this orbit. Okay, let me call this Rm to denote the radius vector after a month. And again, I am going to allow the radius vector to follow the Earth's position for 2 days. Okay, so after a couple of more days, let us say the Earth has gone forward on the orbit a little bit, and this distance is Rm2. Okay, so this is where the Earth is 1 month and 2 days from now. Okay, so again you see that there is some area that is swept by this radius vector. So this is again some area corresponding to 2 days of Earth's motion. What Kepler says is that both of these areas need to be the same, which means that if the planet is closer to the Sun, it moves faster along the orbit. If it is farther away from the Sun, it moves slightly slower. It adjusts its velocity such that the area that its radius vector sweeps in a unit amount of time stays constant. This is Kepler's second law, the law of equal areas in equal time. So let us recap the two laws that we have discussed so far. The first law is the law of elliptical orbits. The second law was slightly complicated. It said that the radius vector of the planet sweeps equal areas in equal time. So equal areas in equal time. The third law deals with the duration of the revolution of a planet around the star. So if I say that a planet goes around in an elliptical orbit, we discussed that the longer of the two axes is called the major axis, and the half of this major axis is called the semi-major axis. Let us say that its length is a. Mind you, this is not the distance between the star and the planet. So we were saying that the sun sits on one of the foci. That is not the distance we are measuring. We are measuring the distance of the semi-major axis. And let us say that this planet takes a time period of capital T to complete one cycle of revolution around the star. Then Kepler's third law states that T squared is directly proportional to A cube. The square of the time period of one revolution of this planet around the sun is proportional to the cube of its semi-major axis. T squared is directly proportional to A cube. So if the semi-major axis of the planet was larger, it would take longer time to finish one cycle of revolution. So these are the three laws of planetary motion as proposed by Johannes Kepler. On this background, now here comes Newton and the story of how the apple fell on his head and gave him an idea to discover the law of gravitation. So Newton by this time had already established his three laws of motion. The one where an object at rest or in the state of uniform motion continues to remain at rest or in the state of uniform motion unless acted upon by an external force. The second law of motion was that the force is equal to the time rate of change of momentum. And the third was of equal and opposite reaction. So if one body exerts a force F on another, then the other body will also exert force F in the opposite direction on the first body. Okay. With this understanding, Newton observed that for an apple to actually fall towards the earth, there has to be some force that acted upon the apple. So there should be a force. That is the first observation. With some information about the acceleration, he guessed that the force has to be inversely proportional to the square of the distance between the apple and the center of the earth. Is proportional to 1 by r square. This is an important contribution. So for example, if I have a body of mass m1 and another body of mass m2 which are separated by a distance r, please note that the distance r is measured from the centers of these two bodies. So if this distance is r, then the force acting, the attractive force which acts between m1 and m2, the gravitational force which must be acting between the two objects of mass m1 and m2 has to be inversely proportional to the square of the distance. So F here is inversely proportional to 1 by r square. Okay. Newton also observed that the acceleration due to gravity remains constant irrespective of the mass of the object. So therefore the force, which is mass times acceleration, will be proportional to the mass of the object. So this is an important observation. Force is proportional to m. Let us say the earth is a big object of capital mass m and a tiny object of mass m1 small m, let us say, is accelerating towards earth due to gravity. Then the force of gravity between earth and this object will be F, which is proportional to m and inversely proportional to r square. Now Newton's third law says that if the earth is exerting a force F on this object, then this object is also exerting a force F back on earth in the opposite direction. Therefore, to make this force symmetric, Newton proposed that the gravitational force F is proportional to capital M into small m by r square. Now since there is a proportionality sign, there will be a constant of proportionality. And since we are studying gravitation, let us call that constant of proportionality capital G. So F is equal to capital G into m into small m by r square. This is Newton's law of gravitation. It turns out that this law is universally true. This is what Newton proposed, that the law which governs the gravitational force between the apple falling towards the earth has to be the same law which governs the force that the earth exerts on the moon. And all such celestial bodies exert a force which is governed by the same law on each other. Okay, so Hunt began, what is the value of this gravitational constant G? And after several hundred years, over 100 years, nearly 100 years, Cavendish came up with an extremely uh, sensitive experiment to find out the constant this gravitational constant. Although we will not delve into his experimental setup, it involved um, measuring the torque that heavier objects would exert on light floating objects, and he measured the angle that this torque would generate. So he eventually found out that the gravitational constant G is actually equal to nearly 6.67 into 10 to the minus 11 Newton meter square per kg square. And there you have it, the universal law of gravitation. The force exerted by any two objects of mass m1 and m2 is proportional to the product of the masses, inversely proportional to the square of the distance between them multiplied by the gravitational constant. F is equal to G m1 m2 upon r square.